How can you prevent derivative kick in PID controllers? Imagine you're trying to keep a robot arm steady, but suddenly a quick change in the target position causes a huge jump in the control signal. That sudden spike is called derivative kick, and it can make your system behave erratically. Now, how do engineers stop this from happening? Let's find out. First, instead of applying the derivative action directly to the error, you can apply it only to the process variable, which is the actual measured signal. This way, the derivative responds only to changes in the process, not to sudden setpoint jumps. It's like focusing only on what's happening in the system, not on the commands sent to it. Another method is to modify the PID algorithm by adding setpoint weighting. This means you give less importance to the setpoint in the derivative calculation. You can assign a smaller weight or even ignore the setpoint altogether, so the derivative only reacts to changes in the process variable. This reduces the spike caused by abrupt setpoint changes. Filtering the derivative term with a low-pass filter is also very effective. Since the derivative acts like a high-pass filter, it amplifies noise and sudden changes. By smoothing the derivative signal with a low-pass filter, you prevent sharp spikes in the control output. Think of it as adding a gentle blanket over the derivative signal to keep it calm. Using advanced PID structures like 2-degree of freedom controllers can help too. These controllers separate the setpoint and feedback paths, so the derivative action is isolated from the setpoint changes. This way, the controller can respond quickly to disturbances without reacting strongly to setpoint steps. In digital control systems, software techniques can be employed. These include algorithms that exclude setpoint changes from the derivative calculation or add anti-windup and filtering features. This makes it easier to implement these improvements without changing hardware. Finally, adaptive tuning methods can be used. These techniques automatically adjust the derivative gain and filtering parameters based on how the system is behaving. They help keep the control smooth even when the system conditions change unexpectedly. In real-world applications like motor speed control or temperature regulation, preventing derivative kick means smoother responses and less wear on equipment. For example, when controlling temperature, applying the derivative only to the measured temperature rather than the setpoint change results in more stable heating or cooling. The main idea is to keep the derivative action focused on the process signals, not on abrupt setpoint changes. Whether through filtering, algorithm tweaks, or special controller designs, these methods help your control system stay steady and reliable.